Out in the silent, unending darkness of space, something new is looking back at us. It is a creation of human hands and minds, a marvel of engineering sent on a mission of pure discovery. This is the James Webb Space Telescope. It is our new eye on the universe, designed not just to see farther, but to see differently. For decades, we have looked up at the heavens and wondered about the great cosmic story. We have pieced together tales of creation, of birth, and of death on a galactic scale. The Webb telescope was built to read the unwritten pages of that story, to capture light that has traveled for billions of years, carrying with it the secrets of the very first stars and galaxies. It is a time machine in a way, showing us what the universe looked like in its infancy. The desire to build such a powerful instrument came from a simple yet profound human need, the need to know. We wanted to understand where we came from, not just as a species, but as a planet, as a solar system, as a collection of atoms forged in the hearts of long-dead stars. Previous telescopes like the venerable Hubble showed us a universe of breathtaking beauty and complexity. But Hubble sees primarily invisible and ultraviolet light, the same kind of light our eyes perceive. To see the unseen, you must build an extraordinary machine. The James Webb Space Telescope is precisely that. At its heart is a magnificent primary mirror stretching 6.5 meters or about 21 feet across. It is not a single piece of glass. Instead, it is composed of 18 individual hexagonal segments, each one meticulously crafted from beryllium, a metal that is both incredibly strong and remarkably lightweight. These segments are coated with a microscopically thin layer of pure gold, a material chosen because it is exceptionally good at reflecting infrared light. Together, these golden hexagons work as one, a giant honeycomb designed to catch the faintest, most ancient whispers of light traveling across the universe. To shield the telescope, engineers designed a colossal sunshield the size of a tennis court. It is made of 5 layers of a special material called capton, each layer as thin as a human hair. The telescope does not orbit the Earth as Hubble does. Instead, it resides in a special place in space, nearly 1 million miles away. This location is known as the second Lagrange point, or L2. It is a point of gravitational stability, where the pull of the Sun and the Earth are balanced in such a way that the telescope can maintain a fixed position relative to them. From this distant outpost, Webb can keep its sunshield constantly blocking out light from the inner solar system, giving it an unobstructed, panoramic view of the cosmos. All the light gathered by the golden mirror is funneled into a suite of 4 highly advanced scientific instruments. These are the true brains of the operation. There is the near-infrared camera, which acts as the telescope's primary imager, capturing stunningly detailed pictures of the universe. The near-infrared spectrograph breaks the light down into its constituent colors, revealing the chemical composition, temperature, and motion of celestial objects. Together, these instruments give us a comprehensive view of the infrared universe, a dimension previously hidden from our sight. For as long as we have known of its existence, Neptune has been a world of mystery. It is the most distant planet in our solar system, an ice giant orbiting the Sun in the cold, dark frontier. It is so far away that it takes light more than 4 hours to travel from the Sun to its cloudy shores. Before the James Webb Space Telescope, our best views of this remote world came from 2 key sources. The first was the Voyager 2 spacecraft, which flew past the planet for a brief but glorious encounter back in 1989. For a few fleeting hours, it gave us our first and only up-close look at this blue giant, revealing a dynamic world of swirling clouds and ferocious winds. Most famously, they revealed a massive storm system, a swirling vortex dubbed the Great Dark Spot, similar to Jupiter's Great Red Spot. This storm, large enough to swallow the entire Earth, was a sign of a powerful and active atmosphere driven by an unknown internal heat source. Voyager also discovered faint, wispy rings around the planet and a handful of small, icy moons. In the decades that followed the Voyager encounter, our view of Neptune came from powerful ground-based observatories and the Hubble Space Telescope. These instruments allowed us to monitor the planet from afar, tracking the changes in its atmosphere over time. We watched as the Great Dark Spot vanished, only to be replaced by new storms that appeared and disappeared in its northern hemisphere. We learned that Neptune has the fastest winds in the solar system, with gusts reaching over 1,200 miles per hour. Then, in the late summer of 2022, the James Webb Space Telescope turned its golden eye toward Neptune. And in an instant, everything we thought we knew about its appearance was transformed. The first images that came back were not of a deep blue orb, but of a glowing, pearlescent world, shimmering with an ethereal white light. This was Neptune seen through the power of infrared, a view that strips away the familiar colors and reveals the underlying structure and heat of the planet. Webb sees light that is invisible to our eyes, and in doing so, it provides a completely different kind of information. It showed us a Neptune that was both familiar in its form, but startlingly new in its details, a world of intricate light and shadow. The most immediately striking feature in Webb's new portrait was the planet's rings. For decades, these rings had been faint and difficult to see, even for our most powerful telescopes. But in Webb's infrared vision, they blazed with startling clarity. For the first time since the Voyager 2 flyby, we saw the complete ring system in stunning detail. The narrow, bright rings and the fainter, dusty bands were all there, encircling the planet like a delicate, glowing halo. Webb's view also gave us a new perspective on the planet's turbulent atmosphere. Instead of the familiar blue, we saw a globe marked by bright spots and bands. These bright patches are high-altitude clouds of methane ice, which are very effective at reflecting sunlight before it can be absorbed by methane gas deeper in the atmosphere. It revealed a bright band of clouds circling the planet's equator, a feature never seen with such clarity before. The rings of Neptune have always been a puzzle. When they were first discovered, they appeared to be incomplete arcs rather than full circles, a strange and unique feature in our solar system. The Voyager 2 flyby in 1989 confirmed that they were indeed complete rings, but they were clumpy and uneven, with some sections much brighter than others. The James Webb Space Telescope has now brought these ghosts into the light. With its unprecedented infrared sensitivity, Webb has delivered the clearest and most detailed view of Neptune's rings since their discovery. In the Webb images, the rings are not faint or ghostly at all. They are sharp, bright, and continuous. We can clearly distinguish the narrow, dense rings from the broader, more diffuse sheets of dust that lie between them. What Webb's infrared vision reveals is the composition of the rings. Different materials reflect infrared light in different ways. The brightness of the rings in Webb's images suggests they are rich in microscopic particles of ice and dust. Are they made of water ice like Saturn's glorious rings, or are they composed of darker, more carbon-rich materials mixed with frozen gases? The crispness and completeness of the rings suggests they may be more stable and perhaps older than previously thought. The images also show some of the fainter dust bands that fill the gaps between the main rings, providing a more complete picture of the entire ring system. It tells a story about the complex gravitational dance between the planet and its many small moons, which act as cosmic shepherds, shaping and sculpting the rings over millions of years. Neptune's atmosphere is a place of extreme violence and constant change. It's home to the fastest winds in the solar system, a turbulent cauldron of hydrogen, helium and methane. Our previous views, mostly in visible light, showed us the top layer of this chaos, the blue haze and the great dark spots that churned within it. But what drives this activity on a planet so far from the Sun has long been a mystery. Webb, by seeing in infrared, peers deeper beneath the surface haze. It sees temperature variations, and where there are differences in temperature, there is energy. Webb's images are essentially weather maps, showing us the engine of Neptune's climate in action for the first time. The bright spots that dot Webb's images of Neptune are high-altitude methane ice clouds. These clouds form where plumes of gas from deep within the planet rise, cool and condense. In visible light, they appear as bright white streaks against a blue background. In the infrared, they are even more prominent because they reflect sunlight with extreme efficiency. One of the most intriguing discoveries from the Webb images is a previously unseen band of bright clouds encircling the planet's equator. This feature hints at a global circulation pattern. a kind of atmospheric jet stream that funnels warm gas up from the planet's interior. This continuous band suggests a powerful and stable weather system that is fundamental to the planet's climate. It may be the very engine that drives Neptune's supersonic winds. Understanding this global circulation is key to solving the puzzle of Neptune's internal heat. By studying these atmospheric features in such detail, we can build better models of how ice giant atmospheres work. This is important not just for understanding Neptune, but for understanding the thousands of Neptune-sized exoplanets we have discovered orbiting other stars. What we learn about the weather on Neptune can be applied to worlds light-years away. Among Neptune's 14 known moons, one stands apart: Triton. It's a world of profound weirdness and beauty, and in the James Webb Space Telescope's portrait of the Neptune system, it shines with an almost unnatural brilliance. Triton is large, nearly the size of our own moon, but it orbits Neptune in the wrong direction. This retrograde orbit is a telltale sign that Triton is not a native moon of Neptune. It wasn't born from the same disk of gas and dust that formed the planet. Instead, it's a captured wanderer, likely a dwarf planet from the Kuiper Belt, the same icy realm that is home to Pluto. Sometime in the distant past, it strayed too close to Neptune and was snared by its gravity. In Webb's infrared image, Triton dramatically outshines its parent planet. The reason for this lies on its surface. Triton is one of the coldest objects in our solar system, with surface temperatures plummeting to around -391 degrees Fahrenheit. Its surface is covered in a thick layer of frozen nitrogen, which acts like a pristine, freshly fallen snow. This frozen nitrogen is incredibly reflective, bouncing about 70% of the sunlight that hits it back into space. This intense brightness, however, is more than just a curiosity. It allows Webb to study Triton's composition in great detail. By using its spectrographs, Webb can analyze the light reflecting off Triton's surface and atmosphere. Voyager 2 gave us tantalizing glimpses of ice volcanoes, or cryovolcanoes, erupting plumes of nitrogen gas and dark dust from beneath the surface. The story of Triton is the story of a captured world, a refugee from the outer solar system. Its capture would have been a cataclysmic event, profoundly disrupting Neptune's original system of moons and rings. Understanding Triton's composition and history helps us piece together the violent and chaotic early days of our solar system's formation. It's a relic from that bygone era, preserved in a deep freeze. The new discoveries from the James Webb Space Telescope are more than just beautiful pictures or isolated facts about a distant planet. They represent a fundamental shift in our ability to study the outer solar system. For decades, our knowledge of the ice giants, Neptune and Uranus, has lagged far behind our understanding of the gas giants, Jupiter and Saturn, and the terrestrial planets like Mars. Webb has now closed that gap. These findings force us to rethink our models of how planets form and evolve. The clarity of Neptune's rings, the complexity of its atmospheric circulation, and the stark brightness of Triton all provide new data points that must be incorporated into our theories. Each new detail from Webb acts as a crucial test for our scientific ideas, showing us where they hold up and where they need to be revised. Furthermore, the study of Neptune is profoundly important for understanding planets beyond our solar system. A large fraction of the exoplanets discovered so far are of a similar size and mass to Neptune and Uranus. By providing such a detailed look at Neptune, Webb is giving us a vital reference point, a Rosetta Stone for interpreting the data we collect from these distant worlds. What this new chapter really signifies is the power of seeing the universe in a different light. By shifting our gaze from the visible spectrum to the infrared, we are not just seeing more, we are seeing differently. We are uncovering processes and structures that were previously invisible. The journey of discovery does not end with Neptune. The images of this distant ice giant are just one small part of the James Webb Space Telescope's grand mission. Its golden eye is now sweeping across the cosmos, from the nearest planets to the most distant galaxies. It's studying the atmospheres of worlds orbiting other stars, searching for the chemical building blocks of life. It's peering back in time to the cosmic dawn, capturing the faint light of the very first stars as they ignited in the darkness after the Big Bang. The future of space exploration will be built upon the foundations that Webb is laying today. Its discoveries will inspire the next generation of scientists and engineers to dream up new missions and new technologies. Perhaps one day we'll send a dedicated orbiter to Neptune and Uranus, a probe designed to dive into their atmospheres and map their mysterious interiors. The telescope is not just an endpoint, it's a catalyst, sparking new curiosity and pointing the way toward future exploration. This relentless pursuit of knowledge is one of the most noble expressions of the human spirit. We explore not for conquest or for profit, but for the simple, profound joy of understanding. We look to the stars because we are a part of the universe, and in learning about the cosmos, we learn about ourselves. The quest to understand our origins and our place in the grand scheme of things is a journey that connects us all, across cultures and across generations. So as we marvel at these new views of Neptune, we are also looking at a reflection of our own potential. We are a species capable of building machines that can travel 1,000,000 miles from home and look back 13 billion years in time. We are capable of working together to achieve goals that once seemed like science fiction. The universe is vast and our time in it is short, but in that brief span we have the privilege of being able to ask questions about it all, and little by little, to find the answers. The story of space exploration is far from over. There will always be another veil to lift, another mystery to solve. The horizon is and always will be endless.